We have now expanded quite a bit of time and effort providing ourselves with tools for analyzing how perturbing forces and potentials will affect our two-body orbits. However, to actually use these tools, we have to describe some actual perturbing forces or potentials, and that is where our focus will shift to now. And we will start by still considering only gravitational forces, but now we will get away from the idealization of the two-body problem and consider more physical systems. Remember, Newton's laws apply only to point masses, and so our formulation of the two-body problem was that of two point masses in space interacting via gravity only. Any point mass can be replaced with an ideal spherical mass distribution, which can equivalently be treated as a point mass because the effects work out to be the same. However, most objects are not uniform density perfect spheres. And so what we will consider now are the gravitational effects and the gravitational potentials of distributed masses. Here we have our two-body system where M2, our smaller orbiting mass, is still treated as a point mass, but M1 is now replaced with an arbitrary body, which we will call script B. Newton's law of gravity can be applied equivalently to every infinitesimal mass element, dm, comprising this distributed mass, B. This differential mass element has a force df, dm, on M2, and this can be written by applying Newton's law of gravity as g times the product of M2 with that differential mass element divided by the separation distance between them cubed in the direction of the separation distance. The full force on M2 due to M1 is therefore the integral over the full mass distribution, which we know in general to be three-dimensional, and hence the triple integral over the extent of the body of the differential force due to this differential mass element. This is gravity, it is a conservative force, and so we know that we can write this as the gradient of a potential, which we will call U, and the full potential is likewise the gravitational constant times this triple integral of dm over the individual potential of each term, which is just the separation distance norm between them, analogous to how the gravitational potential of a point source is mu over r. We should note here that we are absorbing our negative into the potential u. So remember, f is the negative gradient of the potential function v, and we are defining u such that the negative is absorbed into it. And it should also be noted that these integrals are extraordinarily hard to carry out. It is quite difficult for an arbitrary body to establish a mass distribution. If the body is constant density, then typically we will rely on the volume distribution of the body, which is somewhat easier to describe, but in any case, these are not trivial integrals. However, most bodies have some degree of spherical symmetry. At the very least, most major bodies, due to their own self-gravity, have some degree of spherical symmetry. And so spherical coordinates make a lot of sense for this problem. And so we will describe the position vectors of each of our two objects, M2 and the body B, with respect to some inertially non-accelerating point O, via two sets of spherical coordinates, r, theta, and phi, for the position of our orbiting mass, M2, and coordinates rho, lambda, beta, for the position of a differential mass element, dm, within body B. We assume that the density distribution of body B is given by this gamma. So gamma represents the density distribution of this whole body and is going to be a function of those coordinates. And therefore, we can rewrite our previous expression for the potential u of a body at coordinates r, theta, phi, being affected by the full gravitational potential of this distributed body as the integral over the density distribution over the norm of the separation distance between the second body and each of these differential mass elements times the volume element in these coordinates, which you'll recall is rho squared sine beta, d rho, d beta, d lambda. This denominator term in the integrand, the norm of r dm rel2, can be rewritten as 1 over r, remembering that r is the magnitude of the position vector of r2 rel o, times 1 minus 2 rho, where rho is the magnitude of r dm rel o, over r times cosine of beta minus phi, plus rho over r squared to the negative 1/2 power. This expression is purely a function of the trigonometry of the coordinates and can be verified by plugging in our usual trigonometric relationships. But the important thing here is that we've already seen this. This is a Legendre polynomial generating function. And so we know that we can write this as an infinite sum in the Legendre polynomials with arguments cosine beta minus phi. And so the difference between the zenith angles of these two coordinate sets. Remember also that this series will be convergent for rho over r less than 1. And our approach typically is to put the coordinate system at the origin of the center of mass of the body, of the extended body, and then expand the potential for points outside the body. We are interested in the gravitational potential and equivalently the gravitational forces of this extended body acting on things outside of the body. We are interested in writing force is some gradient of our potential function u. And as there are no masses belonging to the extended body that exist outside of the body, the divergence of this force must be 0. You will recall that the divergence of a vector is given by del dotted into that vector. And in this case, the vector f is itself the gradient of a scalar u. And so the divergence of f is the same thing as del squared u, del squared sometimes being known as the Laplacian. We want this divergence to be 0, and therefore what we've recreated is Laplace's equation, which typically it can be solved by separation of variables, and is a relatively straightforward process when you're dealing with this in Cartesian coordinates, but in spherical coordinates, of course, there are some bookkeeping difficulties. I firmly believe that everybody should solve Laplace's equation in spherical coordinates once in their lives. So let's go ahead and do that now. Our governing equation is del squared u is equal to 0. U is a function of spherical coordinates r, theta, and phi. And we are going to solve this by separation of variables by assuming a form of u that is the product of a function r that is a function of lowercase r only, a function capital theta that is a function of theta only, and a function capital phi that is a function of phi only. Now, let's be very clear here. We have changed coordinates from the previous slide because we are interested in seeing the effects of the mass distribution of this arbitrary body on things outside of the body. So we have moved our coordinate system origin, O, to the center of mass of this body. We have redefined the spherical coordinates r, theta, phi as being the spherical coordinates describing the position of our orbiting mass with respect to the center of mass of this extended body B. And we are now going to be operating in a body fixed frame that is rotating with the body. And this is important because, again, we are trying to capture the specific mass distribution of this body. If we were working in a frame that wasn't rotating with the body, if we were working in one of our inertial frames, then we would be allowing our coordinates to constantly be changing the orientation of our orbiting body with respect to the specific mass distribution of the body. So this is a very key point. When we are doing this here, in the completely general case, we are dealing with a body fixed frame. And when we need to apply this back to our equations of motion, we will need to do a coordinate transformation in order to get things back into an inertial frame, or equivalently to transform our equations of motion into this non-inertial rotating frame. So keeping all that in mind, let's go ahead and perform our separation of variables. Laplace's equation in spherical coordinates takes the form 1 over r squared partial with respect to r of r squared times the partial of our potential with respect to r plus 1 over r squared sine phi times the partial in phi of sine phi partial of u with respect to phi plus 1 over r squared sine squared phi second partial in u with respect to theta. Remember that if you don't happen to recall this specific form, you can always get to it by writing out the Jacobian of the coordinate transformation from Cartesian coordinates to spherical coordinates, and then working through the algebra to get to these isolated terms in the partials with respect to the spherical coordinates. We take our separated version of the potential u, plug them into this equation, and we write we are once again using the shorthand S sub phi is the sine of phi and C sub phi is the cosine of phi. And we've replaced the partials with total derivatives because remember, the whole point of doing the separation is that each of these functions, capital R, capital theta, capital phi, is a function of their respective coordinates only. So Laplace's equation in spherical coordinates has the form second derivative of capital R in R times theta times phi plus 2 over R times the first derivative of R in R times theta times phi plus 1 over R squared sine squared phi times the second derivative of theta in theta times phi R plus the cosine over R squared sine phi times the derivative of capital phi with respect to phi times theta R plus 1 over R squared second derivative of phi in phi times theta times R is all equal to 0. We are now going to multiply this entire expression by R squared sine squared phi over the product of the three separated variables, so the equivalently divided by u itself, and that will give us this expression here. We've also collected all of the terms belonging to each of the original partial derivatives, and we see that we have these three sets of equations. For our first separation, we are going to use separation variable negative m squared, and we're going to set this third term, 1 over capital theta times the second derivative of theta with respect to coordinate theta, equal to negative m squared. This is a harmonic oscillator expression. We know that the standard solution for this has the form a sub m for some constant a sub m times e to the I m theta, and m here can take any value from negative infinity to infinity. Alternatively, we can use Euler's formula to rewrite this complex exponential as the sum of cosines and sines in m theta, and then we will have two sets of constants c sub m and s sub m, and you'll notice that we've absorbed the imaginary value into this s sub m. We can now substitute negative m squared for this third term. We are also going to divide through everything by sine squared phi. So we're dividing by sine squared of phi to cancel out this term, and this term, and one of these terms here. And that allows us to rewrite all of our Laplace's equation in spherical coordinates as this expression here. For our second separation, we are going to choose a separation constant of the form L times L plus 1. And we're going to apply that now to this first set of terms in the derivatives of the R function. So writing this out, we have coordinate R squared times the second derivative of the R function in R plus 2R times the first derivative of function R in coordinate R is equal to L times L plus 1. And if you recall, we had a term of the R function in each of these denominators, which we now bring over to the right-hand side. We do so because this is a known form of differential equation known as Euler's differential equation. And if you're keeping track at home, this is most likely the millionth thing named after Euler that we will have come across in this course. This equation has a solution of the form R is equal to the infinite summation of constant a sub n times R to the n plus c. And in this case, based on the form of our separation constant, we have c times c plus 1 is equal to L times L plus 1, which means that c can be L, and negative 1 only. And therefore, we don't have an infinite summation. We actually just have R sub L of R is equal to a sub L R to the L plus b sub L R to the negative L minus 1. Plugging in this separation constant to replace these two terms, Laplace's equation in spherical coordinates is now 0 is equal to L times L plus 1 minus m squared over sine squared phi, it's this term here, plus all of the remaining terms in the phi function. For our final separation, we are going to define x as cosine of phi, which means that we can rewrite all of this as the derivative in x of quantity 1 minus x squared times the derivative of function phi with respect to x, plus all of these leading terms where this sine squared phi denominator can be replaced with 1 minus x squared. We have also multiplied things through by this phi denominator, and so that is where this phi comes from. This is known as the associated Legendre differential equation, and unsurprisingly is solved by the associated Legendre functions. However, Before we attack the full solution to the system, let's consider a restricted case where our body is azimuthally symmetric. Azimuthal symmetry is very important because it occurs in lots and lots of bodies. Remember, our first cut of the description of the shape of the Earth is as an oblate spheroid. An oblate spheroid has pure azimuthal symmetry. And many, many bodies, especially larger bodies, can be described to first order as azimuthally symmetric. And this vastly simplifies the equations, and so it is worth considering for some preliminary analyses. So the azimuthally symmetric case is the case where the theta function is strictly 1, which corresponds to a separation constant m of 0. The associative Legendre differential equation in this case collapses down to the Legendre differential equation, which we've already seen, and which we know to be solvable by the Legendre polynomials. We've previously discussed the nature and the ways that we have to manipulate Legendre polynomials. One other thing to note is that the Legendre polynomials form a complete orthogonal set on the domain of -1 to 1, which matches the range of cosine phi, which is the argument to our polynomials in this case. What that means is that we can write for any pair of Legendre polynomial indices L and L prime, the integral over the full domain of -1 to 1 of the product of two of these polynomials evaluated at the same argument x multiplied by this normalization will have to be 0, which is the same as the integral from -1 to 1 of the product of these two polynomials, which equals 2 over 2L plus 1 times the Kronecker delta of L prime L. Thus, these polynomials are also a basis for all functions defined within this range of -1 to 1. And so in general, we can write any function f of x defined on -1 to 1 as the sum from k equals 0 to infinity of a constant a sub k times the kth Legendre polynomial in x, where these a sub k's are given by this normalization. Each a sub k is 2k plus 1 over 2 times the integral from -1 to 1 of the function f of x multiplied by the kth Legendre polynomial. This is very similar to, for example, the Fourier basis, but is a different basis set and is on a limited domain rather than the fully infinite domain. Therefore, the general solution for an azimuthally symmetric body gives us the potential, which is a function of r and phi only because it is independent of the theta variable, as the sum from L equals 0 to infinity of a sub L r to the L plus b sub L r to the -L minus 1 of the Lth Legendre polynomial in cosine phi. We wish to impose the boundary conditions such that u goes to 0 in the limit where r goes to infinity. Remember the physics of this. R is describing the magnitude of the orbital radius of our orbiting mass m2 about the extended central body. We need gravity to go to 0 as the separation distance between bodies goes to infinity. And so in the limit, as we take this magnitude to infinity, we require that u goes to 0. The only way that we can make this true is to get rid of this term, because this term, as L goes to positive values, will grow without bound. And so the only way that we can get an infinite R to give us a 0u is to set all of the a sub L's equal to 0. This term is okay because this is the reciprocal of R. L is strictly positive, and so this will be an increasingly small quantity as R goes to infinity. The b sub L coefficients will have to be determined by the density distribution and shape of the body. And so we can write the potential of an azimuthally symmetric body acting upon an orbiting body whose position with respect to the center of mass of the extended body is given by spherical coordinates r and phi, where phi is a zenith angle, is equal to the gravitational constant times the total mass of that central body, which we call m sub b, divided by the orbital radius magnitude r times 1 minus the sum from k equals 2 to infinity of constants j sub k times the equatorial radius of the body, which we will call r sub b, divided by the orbital radius magnitude r to the kth power times the kth Legendre polynomial in cosine of the zenith angle. One really important other note, we developed this expression starting with the definition of these coordinates in explicitly a non-inertial rotating frame. However, if the body is azimuthally symmetric, as long as we are working in the equatorial frame of the body, then it does not matter whether we are describing these components in an inertial frame or a rotating frame, because the results are one and the same. Because the only reason why we cared about being strictly in a body fixed frame is because we wanted to capture the specific mass distribution of this body. But if the body has azimuthal symmetry in the potential, then there is no theta dependence, and it really doesn't matter how the body rotates. The only important thing is that phi is being measured from the axis of rotation, from the pole direction, and by convention, the north pole direction of our body. You will notice that we have transformed this expression slightly, and we have renamed these b sub l's into these j sub k's. These are coefficients named in honor of a mathematician by the name of Harold Jeffreys. J of 0 is equal to 1. That's this term. And because of the symmetry of an azimuthally symmetric body, you can prove that J1 has to be equal to 0. This is because the first Legendre polynomial of cosine phi is equal to cosine phi itself. And the integral over that, the normalizing factor, here will be 0. These J coefficients map to the effects of increasing degrees of non-uniform mass distribution in a latitudinal sense. So the first of these, J2, is the equatorial bulge of the planet and is the primary Earth oblateness term, or any planetary body oblateness term. We can take a look at the values of some of these for solar system bodies, which we have tabulated here, drawing from a variety of different sources. And these are established by placing spacecraft around bodies, either in orbit or via flybys. And you will notice as we get further and further out into the outer solar system, where we've never had something in a permanent orbit, we have less and less knowledge of these things. There are estimates for J3 for Uranus and Neptune, but they're honestly not great. The error bars on them are enormous, and so I've omitted them here. Just by looking at these values, you can instantly tell that for the majority of bodies, the J2 term dominates over all the other terms. For the Earth, for example, J2 is a full 3 orders of magnitude bigger than the absolute value of J3 and J4. The other thing to note is that these values can be positive or negative. Remember, these are coefficients for an infinite series that is an orthogonal decomposition of a particular potential function. And so just like with any basis set, we are building up our final answer by adding and subtracting scaled values of each subsequent basis element. So for the Earth, for Mars, for the Moon, and for Jupiter, Saturn, Uranus, and Neptune, and to a lesser degree, Mercury, we have J2 being the strictly dominant term. An interesting thing happens for Venus, for example, where J2 is pretty much the same order of magnitude as J3 and J4. Remember, Venus is barely rotating as compared to these other bodies. A day on Venus is about 116 Earth days, whereas a Venus year is about 225 Earth days. And so compared to something like the Earth, which completes 360 plus revolutions per orbital period, Venus is barely making 2 revolutions per orbital period. The fundamental oblateness of these bodies is caused by the flattening due to their relatively rapid rotation. This is especially the case for Jupiter, which is spinning at an enormous rate about its axis as compared to its orbital rate, and similarly for Saturn. Bodies that are barely rotating, like Venus, like Mercury, and to a lesser extent the Moon, which has a rotational period of 28 days, you see much less of this discrepancy between the J2 values and the higher order Jeffreys numbers. A lot of our preliminary orbital analysis and perturbation analysis really just focuses on the oblateness terms. And this is particularly true for things like the Earth, where J2 is so dominant. To get a completely accurate picture, you need all of the terms to a much higher order And you also need to go to a non-azimuthally symmetric treatment. But as a first cut, just using the J2 term and ignoring everything else will give you some pretty strong predictive power.